Alright, today we're going to start section 7.2, which is going to be logarithmic functions. So we want to understand the relationship between an exponential and a log function, understand the basic properties of logs and their graphs, know what the common log and the natural log are. Most of this stuff should be review, and we covered some of this at the very beginning of the year, so keep in mind always that those videos are still on YouTube, so if you want to look at those again with the log properties, you can always view those at your leisure. So, find the inverse of f of x equals 3 to the x. Well, what do we do to find an inverse? Well, normally we switch the x and the y. So we're saying, x equals 3 to the y, and then we try to solve for y. Well, how do I solve that for y? I can't solve it for y unless I change this into a log function. So this becomes log base 3 of x equals y. Now the other way to go about this would be graphically. So remember that a function and its inverse reflect over the line y equals x. So if we have, let's say, x and then f of x when x is -1, this is going to be 1/3 at 0 and 1 and 2. So at 0 it's going to be 1, at 1 this will be 3, at 2 this will be 9. So if I take those values, let's plot those. So -1 we've got like 1/3 there, 1 is 3, 2 is 9. I can draw that lovely graph. Perfect. And now I know that those values are going to flip over the line y equals x. So there's my line y equals x, a little sloppy, but you'll get the idea. So for instance, f inverse, instead of having the point 0, 1, I'm going to have the point 1, 0. Instead of having the point -1, 1/3, I'm going to have the point 1/3, -1. Instead of having the point 1, 3, I'm going to have the point 3, 1. Instead of having the point 2, 9, I'm going to have the point 9, 2. So my inverse, which is the log graph, is going to look like this. Wow, that's lovely. And another thing to point out, so on the exponential function, we have that horizontal asymptote of y equals 0, which translates to the log function. We now have a vertical asymptote of x equals 0. So we want to keep in mind, I know I pointed this out at the very beginning of the year when we did our summer review unit, but that is that you cannot trust your calculator to do a log graph for you. It'll show you only some of the graph, but because of this vertical asymptote, it's not going to show you everything. So you need to understand that the function is going to continue on forever to negative infinity. So, if we say f inverse of x is log base 3 of x, well then the domain now, remember the domain and range switch, so the domain is going to be 0 to infinity. The range is negative infinity to infinity. We have a vertical asymptote of x equals 0. I have a y-intercept now of none and an x-intercept of 1, 0. So these are all switched from what it was for the exponential function. So this leads us to our general definition of a logarithmic function. For x is greater than 0, a is greater than 0, and a does not equal 1. Y equals log base a of x, if and only if x equals a to the y. Remember, I did mention this again at the beginning of the year. Being able to switch from an exponential function to a log function and from a log function to an exponential function is the most important part of this entire unit and this chapter. If you can't do that, then there's very little that you're going to be able to do with logs and exponentials. So you really want to understand that when you translate from one to the other, the base stays the same. What you're taking the exponential of becomes what the log equals, what you're taking the log of becomes what the exponential equals, and vice versa. So, use the definition to evaluate the following. F of x equals log base 4 of x when x is 16. F of x equals log base 2 of x when x is 64. F of x equals log base 5 of x when x is 1. And f of x equals log base 3 of x when x is 1 over 81. I want you to pause the video, evaluate those, unpause when you're ready to check your answer. Okay, so you should be able to actually do all of these in your head, but I will show you the work if you were confused. F of x equals log base 4 of 16. Well, I can rewrite that as an exponential, and that's 4 to the y equals 16. So 4 to what power equals 16? 4 squared. So y equals 2. F of x equals log base 2 of 64. 2 to the y equals 64. So 2 to the what power equals 64? That's 2 to the 6th. F of x equals log base 5 of 1, so 5 to the y equals 1, 5 to what power equals 1, anything to the 0th power is 1, so y equals 0. And then the last one, f of x equals log base 3 of 1 over 81, so 3 to the y equals 1 over 81, so y to what power equals 1 over 81? Well, since this became a fraction, I know it needs to be a negative exponent, so it's y equals negative 4. Alright, so next I want you to write each of these logarithmic equations as exponential equations, and then solve for y. So pause the video, unpause when you're ready to check your work. Alright, so y equals log base 2 of 16 becomes 2 to the y equals 16, so 2 to the what equals 16, y is 4. Y equals log base 2 of 1 half becomes 2 to the y equals 1 half, so y equals negative 1. 5 equals log base y of 17, so y to the 5th equals 17. How do I solve that? Take the 5th root of both sides, so y equals the 5th root of 17. One thing I do want to point out, so for instance, this right here, we're not going to get into these properties of logs today, but we have seen them already. So I want to understand that this can also be written as y equals log base 2 of 1 minus log base 2 of 2. And then you'll see log base 2 of 1, 2 to the what equals 1. So this would be 0, 2 to the what equals 2. That's going to be 1. So we get negative 1. That's another way to do this. If you don't understand that part right now, even though we did cover it at the very beginning of the year, that's okay. It's more important that you understand how to turn it to an exponential and solve that way at this moment. Alright, so then this leads us to basic properties of logs that we should already understand, but if we don't, we'll go through them again. So log base a of 1, what does that equal? That's saying a to what power equals 1. Well, anything to the 0th power equals 1. Log base a of a, that's saying a to what power equals a. So that's going to be 1. Log base a of a to the x is going to be x. For right now, I'm just going to leave it at that. We can prove it later. We do know the properties to prove it, but I'm not going to go through that right now in this video. Hopefully you understand that though. And then a to the log base a of x is also going to be x. And then the last one, this is very important when we get to solving log equations. If log base a of x equals log base a of y, then we know x has to equal y. Okay, so now you're asking yourself, is there a log that perhaps appears more often or is more useful than other logs? And the answer to that is yes. We call that the common log, which is log base 10. So this is the log button on your calculator. Alright, so I want you to use your calculator to evaluate each of these three. The first one you actually should be able to do without a calculator, but just for practice you can use the calculator. So we don't need to type in the base because the log button is telling us base 10. So this is just saying log of 100. We hit enter, we get 2. That should make sense because we know 10 to the second power is 100. So I want you to go ahead and do the rest of these. Shouldn't take you very long. Unpause when you're ready to check your work. Okay, so these are the values you should have gotten. Log base 10 of 2/5 is negative 0.398. Log base 10 of 5, this when you first look at it, you think it's going to be a nice number because you're thinking 10 and 5 have relationships. but 10 to the what power equals 5? It's not a nice number. It's an irrational number. It's going to be 0.699. And then log base 10 of negative 4. If you type that into your calculator, log negative 4, you get non-real answer. And that's because, why? Because this is outside of the domain of the log function. Remember, our domain was 0 to infinity. Alright, so then the next burning question is there a log that just seems more natural? And of course the answer to that is yes as well. That's going to be the natural log. Well, where do we get that? We get that by rewriting f of x equals e to the x as a logarithm. And so that becomes the natural log. And so if we rewrite that as an exponential, we get f of x equals log base e of x. We shorten this by writing ln of x. So f of x equals log base e of x is the same as ln of x. Those are what we call the natural log. Obviously x still has to be greater than 0. That's, this is the natural log. The most common confusing thing about natural log is people think that it's something different. It still follows all of the properties of logs. It is a log. It's just used so often. It's not the common log, but it's used so often that it has its own little notation, ln of x, so that we don't have to write the little base, because that gets confusing whenever we have to write the base as a subscript, and a lot of times we write it kind of sloppy, at least I do. So it's a lot nicer just to be able to write ln of x because we use it so often. The natural log follows all of the same properties of regular logs, again, because it is a regular log. So the natural log of 1, e to the what equals 1, e to the 0 equals 1. The natural log of e to the what equals e, e to the first equals e. The natural log of e to the x, that's the same thing as saying log base e of e to the x, so we know that's x. E to the natural log of x, that is also x. And we know if the natural log of x equals the natural log of y, then x has to equal y. Okay, so next I want you to rewrite the log equations as exponential equations, and then rewrite the exponential equations as log equations. You are not solving anything, you're just rewriting. Pause the video, unpause when you're ready to check your work. Okay, so I know if the natural log of 4 equals 1.386294, then e to the 1.386294 equals 4. I know if the natural log of 5/8 is negative 0.47000036, then e to the negative 0.47000036 is 5/8. I know that if e to the negative 4th is 0.0183156, then the natural log of 0.0183156 is negative 4. And I know that if e to the 3/4 equals 2.117000, then the natural log of 2.117000 is 3/4. Alright, next I want you to find the domain, the asymptotes, the intercepts, and draw a sketch of f of x equals the natural log of 3 minus x. Pause the video, unpause when you want to see your work, or want to see the answers, I guess. Okay, so there's a few ways in which I can go about this. One, I can understand my transformations. This is going to shift left 3, and I'm going to divide the x values by a negative 1. Another is to find a couple of points. Well, what points do I want to look for? Well, I want to look for the x-intercept because it's a log graph. So if I change this into an exponential, I have my work over here on the right. If I make this 0, e to the 0 is 3 minus x. So then I end up with x equals 2. So that's a nice value. Then the other value, which is not nice, is going to be if what's in the parentheses here equals e, because then I have e to the e. So I set 3 minus x equal to e, and I solve for x, and that's how I end up with 3 minus e. So I ended up, and that point is going to equal 1, so I plot those points, and then I draw my curve. My vertical asymptote, it normally is at x equals 0. Now it went left 3, but then reflected over the y-axis to positive 3. So the domain is negative infinity to 3. Y-intercept is going to be, if I plug in a 0 for x, then this just becomes the natural log of 3. That's an irrational number, so just leave it as ln of 3. Okay, last one. So we're given this function which represents the human memory model. It's log base 10. I want you to find what was the average score of the original exam, what was the average score after 3 months, and after 11 months. Pause the video, unpause when you're ready to check your work. Okay, so hopefully this was as easy as it should have been. Plug in 0 for the original exam, plug in 3 for after 3 months, plug in 11 for after 11 months, type this into your calculator. We get 78, 67.765, 59.654. We can see that we are forgetful and that the averages go down over time. Here's your conclusion. Make sure you understand how to switch from a log to an exponential and an exponential to a log. That's the most important thing.